Hi, this is Dan Bullard, retired electronics engineer, sitting on the front deck of my houseboat again. It's a beautiful day. I want to talk to you about THD again. The title of my book, Distortion, is Distortion, the Cause of Harmonics and the Lie of THD. THD is a lie. If you look around to find the THD of a square wave, you'll find various numbers and, measured with this instrument and that instrument. None of those instruments are actually valid. The only way to measure THD, if you want to bother doing it, is by doing an FFT on the captured wave. You capture coherently so that your fundamental and all the harmonics are in individual bins, so that the fundamental is in bin 9, for example, and then the second harmonic is in bin 18, and the third harmonic is in bin 27, and then so on and so forth. That's the only way to do it. And then you can go in and get the peak value. That's what the FFT gives you. Sometimes a peak squared or who knows what. Then you can go in and take the square root of the sum of the squares of some number of harmonics. It's geese time. There they go. So take the square root of the sum of the squares for some number of harmonics. Now I tend to go with 50 harmonics. That's what I do. I like to do that. 9 harmonics is not enough. My compadre Noel, he missed a serious problem with the tester by ignoring the harmonics above the 9th harmonic. So he just used the standard THD function. It said that the THD was this, and then the noise was astoundingly huge. No, that wasn't noise, it was harmonics. But because the THD function, and he didn't understand it, it's just one of these things, guy with a degree doesn't know anything. So he just assumed that the THD function would tell him total harmonic distortion, and then everything after that was considered noise. That's not the way it works. Everything after that is still harmonics and noise, but as most people will tell you, the harmonics roll off a lot. Well, they don't always roll off. It depends on the distortion. And the distortion that Noel saw was not rolling off. It was going on and on forever. And so he kept thinking he was having a noise problem. He wasn't having a noise problem. It was a THD problem. And the engineering manager finally admitted he fucked up. Finally, years later, after the customer spent $500,000 on this tester, and then they found they couldn't use it because it was giving him terrible results. So using a finite number of harmonics for THD is ridiculous, but you have to, because it's the square root of the sum of the squares of some number of harmonics divided by the fundamental amplitude. But what's really interesting, and I talked about this when I covered chapter 2 of distortion, the THD of a square wave. The THD for a square wave, looking at 50 harmonics, is minus 6.5 dB. And I just say that in my book, minus 6.5 dB. But it's 50 harmonics. Now, everybody else measured it with some other number of harmonics. If you do only like 9 harmonics, you get like minus 7 something dB. Other people measure minus 9 dB. Other people claim that the square wave has more harmonic energy than the fundamental. Absolutely not. That doesn't happen. But what's really cool, if you remember, is that I told you the amplitude of the harmonics from a square wave is 1 over the harmonic number. Skip the even harmonics, because there's no even harmonics in a square wave that's 50% duty cycle. So 50% duty cycle square wave, the harmonics roll off at 1 over the harmonic number, but there are no even harmonics. So the even harmonics are minus 300 dB, call it that. The even harmonics are gone. The odd harmonics pop up So the third harmonic is 1/3 of the amplitude of the fundamental, and the fifth harmonic is 1/5 of the amplitude of the fundamental. The seventh harmonic is 1/7 of the amplitude of the fundamental, and so on. That's the Taylor series. So, me calling my laws of harmonics the Bullard laws of harmonics, it's not unusual for people to call things after their own name. So the Taylor series is named for a guy named Taylor. So, Newton's laws of physics, come on. Everybody gets, if you discover something, you get your name on it. And, these people, they think I'm being selfish. Well, I'm not going to name it after Bruce Tibbets, who said I'm an idiot. I'm not going to name it after Tony, who said I'm an idiot. I'm going to name it for myself. Okay, so square wave harmonic roll-off is 1 over the harmonic number. What about a triangle wave? It's a little different. Read chapter 2. But in chapter 2, I evolve a triangle wave into a ramp wave. What is it for a ramp wave? For a ramp wave, the harmonics fall off at exactly the same rate as they did in a square wave. Exactly. The problem is, there's also now even harmonics. So with the ramp wave, the even harmonics show up, and so now the amplitude changes a little bit. So the amplitude of the harmonics is 1 over the harmonic number, but now the even harmonics are included. And there the THD is minus 2.04 dB for a ramp wave. I just did the calculations on it. And I don't have Excel, so how did I do it? It's easy. It's really easy. I use Numbers, which is the Excel version on the Mac. You don't even have to do an FFT. I'm telling you this. For a square wave, it's 1 over the harmonic number. So I can just make that up, 1 over the harmonic number, just have the harmonic numbers listed, 1 over the harmonic number, all the way down, take the square, take the sum, take the square root, and convert it to dB. So that's how I did this. Because I didn't really know, I saw it in the book. I'm like, was that for 50 harmonics minus 6.5 dB? Was that for 50 harmonics or just 9 harmonics? That was for 50 harmonics. How do I know? Because I did it in Numbers, and I didn't even need an FFT. So, apparently most of you are very, very concerned about doing an FFT in Excel. But if you don't want to do an FFT, you can still do this stuff, because you can do stuff in Excel or whatever, Numbers, whatever. So for ramp wave, the THD is minus 2.04 dB. Because the ramp wave has all the even harmonics, the THD is much worse. But now, what is for an impulse? That's the really bad one. For an impulse, the THD is plus 17 dB. So plus 17 dB for an impulse. That satisfies the condition that they said was the distortion for a square wave. The harmonics are bigger than the amplitude of the fundamental. Now, the individual harmonics are not bigger than the fundamental. The individual harmonics are exactly the same size as the fundamental. But if you add them up for 50 harmonics, you get an answer of plus 17 dB. So that's really cool. But what's really interesting is, remember the beauty of the impulse and the square wave and the ramp wave. For the impulse, the harmonics are all exactly the same. For a square wave, it's 1 over the harmonic number, only odd harmonics. And for a ramp wave, it's 1 over the harmonic number, but includes the even harmonics. Now, many people out there think that harmonics are random. I got that from Stack Overflow. Oh, you need to use a random number generator to randomize those harmonics. No, harmonics are not random. Noise is random. Harmonics look random because they don't understand the harmonic signature. The harmonic signature, we saw that in that one video. That guy didn't understand the harmonic signature. He just didn't understand it. He didn't know what that was. That's the Bullard harmonic signature, and I figured out the formula for that. That was my formula based on David Hillel Wilson's formula for calculating the harmonics of a square wave. A square wave is a distorted sine wave. A distorted sine wave is the same thing. The Bullard harmonic solution isn't that different from David Hillel Wilson's formula. And I have to thank David Hillel Wilson, even though he's dead. He came up with a formula that I could use or manipulate and finally come up with the right answer. So, 2 points here. You can use something that's not Excel to do all this stuff, or a lot of this stuff. And the beauty of the math is so beautiful, it's so wonderful. We got a boat coming. Oh, well. These guys, these fishermen, they think they have the fastest fish in the West. Let's see how this goes. Yeah, those are fast fish. Anyway, so the math is beautiful. The square wave, the Taylor series, odd harmonics only for a 50% duty cycle square wave, 1 over the harmonic number. For a ramp wave is basically 1/2 of a square wave. Believe it or not, it's 1/2 of a square wave. So you got one straight edge up going straight up, one sloped edge going down. So it's only got one fast edge, and because it's only got one fast edge, it has both odd and even harmonics. With a square wave, you have 2 fast edges. So there's odd harmonics, but no even harmonics, because it's symmetrical in time. If you go away from 50% duty cycle square wave, you get some different thing, because that's David Hillel Wilson thing. You have to worry about that. But for 50% duty cycle square wave, you get no even harmonics, only odd harmonics. And the harmonics fall off at 1 over the harmonic number. Beautiful mathematics, beautiful. You don't have to measure the square wave, because you're not going to get a perfect square wave. If you get on maybe a teradyne, maybe a real high-speed tester, you can get very close to a square wave. But don't put a spectrum analyzer in a square wave. Don't put a spectrum analyzer in anything. Don't use a spectrum analyzer ever. Use Excel or numbers. With a ramp wave has one slow edge up, one fast edge down, or one fast edge up, one slow edge down. So that is asymmetrical in time. It's the most asymmetrical in time wave you can get, and so it has both odd and even harmonics. Okay, and so the amplitudes fall off the same way, 1 over the harmonic number, but includes even harmonics. And so the THD is minus 2.04 dB rather than minus 6.5 dB for a square wave. For an impulse, all the harmonics are exactly the same amplitude as the fundamental, and that has a THD of 17 dB, plus 17 dB. But that tells you those are the very extremes. So a square wave, a ramp wave, and an impulse. They're the extremes. They follow a very pure mathematical model. And so harmonics are not random. They're not random. I'm not making this stuff up. This is years of experience combined with years of experiments with math, okay? If you don't believe in math, if you're like Tony, or you're like Bruce Tibbets or some of these other guys on Stack Overflow, that you think all this stuff is random, it's not random. It looks random because a Bullard harmonic solution can develop some very strange looking patterns that look random. It's not random. It's not random. These guys don't have a clue. And that's why I'm making these videos, to explain to you these things are not random. They're perfectly mathematical, perfect. And I found the secret to it. Nobody else has, and that's the beauty of it. I love being like, the Newton or the Einstein or the Feynman, better than Feynman of all these things. And it's great, you know. I mean, will my name live in history? Maybe. We can only hope, or I can only hope. I want you to learn from this. I want you to understand and realize, like I said in another video, there's a lot of stuff out there that people rely on this stuff. They think that it's all magic. It's not. It's pure mathematics, just like this stuff is. Pure mathematics. You know, they're not artifacts. Harmonics are not artifacts, and most things in the world are not. They're controlled by physics. And it's a beautiful thing. It really is. And I hope you get to like find something out like that. I hope you get to discover something like that. Anyway, I better go. It's going to get windy here. So once again, from the river, it's Dan Bullard. See ya.